Math 1830, Basic Calculus. Module 1, Pre-Calculus Skills. In Module 1, we are going to review some important pre-calculus topics needed for this class. In Section 1.1, we're going to do laws of exponents. 1.2, we're going to do piecewise functions. 1.3, we're going to do the difference equation. 1.4, vertical and horizontal shifts. And 1.5, rational functions. And we'll start it off in 1.1 with laws of exponents. Law number 0, or the definition of an exponent, states that a to the n is equal to a times a times a n times. Our first example would be a to the third power would be equal to a times a times a. Our second example would be like 3 to the fourth power, which would be 3 times 3 times 3 times 3. So notice that 3 is copied 4 times, which would be equal to 81. If we have negative 3 to the fourth power, that would be equal to negative 3 times negative 3 times negative 3 times negative 3. Again, this would be equal to 81 because there's 4 negative, and we know in multiplication an even number of negatives gives you a positive answer. And last, one that's commonly missed is negative 3 to the fourth power. Here, notice the exponent only copies the 3, but not the negative side. So we would have 4 3's and only 1 negative, which would give us a negative 81. So please note the difference between these two. Our first law that is not a definition states that a to the n times a to the m is equal to a to the n plus m. So let's say we have x to the third power times x to the fifth power. Well, if you look at this, this is 3 x's here, all multiplied together. This is 5 x's here, all multiplied together. So total, that should give us 8 x's multiplied together. That's how this law works. So if we have 3 to the 5th times 3 to the 7th, this answer would be equal to 3 to the 12th. Law 2, we have a to the n to the m is equal to a to the n times m. So let's use x again. Let's say we have x to the third to the 7th. Well, if you look at this, we have 3 x's multiplied together here, copied 7 times. So that would be 21 x's. Let's say we have 2 to the third power to the fifth power. That would equal to, if we have 3 2's and they're copied 5 times, that would give us 15 2's. In law 3, we're dealing with more of division, so we're dealing with cancellation. So we have a to the n over a to the m is equal to a to the n minus m. So let's say we have a to the 7th over a to the 3rd. That would be equal to a to the 7 minus 3 using our law, which would be a to the 4th power. Alright, let's look at the case, and we need to remember this. Let's look at the case where we have a to the 5th over a to the 5th. That would be equal to a to the 5th minus 5th, which would be equal to a to the 0 power. And we need to remember this one for future. And the last, let's say we have a to the 5th over a to the 9th. So that would be equal to a to the 5 minus 9, and we know from integers that this would be equal to a to the negative 4th power. Again, just like a previous example, we need to remember this one. Law 4 says that a to the 0 power is automatically equal to 1, which means that anything to the 0 power, whether it be x to the 0 power, is equal to 1, or 3 to the 0 power is automatically equal to 1. If you'll remember in law 3, we had stated that x to the 5th over x to the 5th was equal to x to the 5th minus 5th, which would be equal to x to the 0 power But we also know that anytime you have two things, the same thing over the top of each other, it's automatically equal to 1. So here we can tie the two ends, which proves this law. So just remember, in the case of law 4, anything to the 0 power is automatically equal to 1. In law 5, we deal with a negative exponent. We say that a to the negative nth power is equal to 1 over a to the n. If you remember from law 3, we had said that if you have a to the 5th over a to the 9th is equal to a to the negative 4th power when you did 5 minus 9. But also, remember division states that if you have 5 a's on top, a to the 5th power, and you have 9 a's on bottom, and we start canceling the things because we know that anything over itself is automatically equal to 1. 5 of the a's, and notice that will leave me with 4 a's on the bottom and 1 times 1 times 1 times 1 times 1 on top, which is 1 over a to the 4th, which proves that these two things must be equal to each other. So all we have to remember is a negative exponent simply means that the base is in the wrong spot on the numerator-denominator line. Let's look at a few examples of this. The first one, let's look at 4 over a to the negative 6 power. Well, since we have a negative exponent here with the a, then what this means is we need to move it upward to the numerator. So it will become 4a to the 6th all over, now remember there's an understood 1 down here, so it's over 1, which is really just 4a to the 6th power. Let's say that we have it on the top. Let's say we have 4a to the negative 6 for our second example. Notice the 4 has an understood exponent of 1, so it stays on the top. But the a has a negative exponent, which means it needs to drop across the numerator-denominator line, becoming a to the 6th on the bottom. So notice again, the negative exponent simply means it needs to be moved across the numerator-denominator line. Last, let's look at one that's got all kinds of movement needed. So if we'll look, notice that both the top x and the bottom x both have negative exponents. So that would become x to the 4th, and the bottom would become x to the 3rd. Notice both of those moved. For the y's, the y to the 5th is going to stay put because it has a positive exponent. But the y to the negative 7th needs to move up to the top because it has a negative exponent. And last, notice that the z to the 5th has a positive exponent, so it'll stay put, but the z to the negative 3rd is going to move downward. Okay, and then notice that using cancellation, if we have 4 x's on top and 3 x's on bottom and they cancel, that's going to leave me with 1 x on top. If we have y to the 5th times y to the 7th, that will give us y to the 12th. And notice on the bottom, if we have z to the 5th and z to the 3rd, that'll give us z to the 8th. And so I think this illustrates, it's a good illustration for negative and positive exponents and how they are affected across the numerator and denominator line. And last, we're looking at bases that have exponents that are fractional. So let's say we have a to the 1/2. Well, really we can write this as notice that the bottom is the root, a, and then the top, the numerator, is the exponent. So really we can just write this because understood 2 is a square root, so that's the square root of a. Alright, let's look at b to the 2/3. So this would be the cube root of b squared. And last, let's go the other way around. Let's go with the fifth root of x squared. So we would write this in fractional notation, x to the 2/5.